Hey everyone, welcome back. We're going to do a video on Coulomb friction. So when I say Coulomb friction, maybe you haven't heard this, maybe you've heard sliding friction or contact friction, something like that. Really what we're talking about is, I'm saying here's an object. This object can be in contact with a surface, right? And as it slides on this surface, there's a little bit of friction. So that's what we want to model, is the sliding friction. I'm going back to an example we did in a previous video. Here's a sliding block. There's some external force acting on it. We know that we can do a free body diagram: external force, gravity, normal force, and then F sub c. So I'm saying that this is a Coulomb friction force. And from this, we can write some forces, we can write some moments. If you write this sum of forces, this is everything that is on the diagram, right? You are not, however, in a broad sense, you are not done. And the reason you're not done is because these two right here, the normal force and then F sub c, you don't want to leave these as they are, okay? This normal force and this F sub c, they need to equal things. N equals Fc equals. And then you write some expression for these, and then you put those back into these equations. You'll see, we'll definitely do this a lot when we get to equations of motion. Now, what is the value of N? Well, if we look at the diagram, and if we look at our sum of forces equation, the only forces in this problem is gravity and the normal force. And if we are assuming that the block always stays in contact with the ground, if the block does not go up and it doesn't go down, then it can't accelerate up or down, which means the sum of forces in the y-hat n direction have to equal 0. So in this problem, it's very obvious what is happening. N is going to equal mag in this problem. Now, I could make this problem more complicated. I could do something as simple as this. I could angle the external force such that the external force now has a portion in the x and a portion in the y. That would make this no longer be true, because now the normal force would have to cancel both gravity and that portion of F external. We could do something else. We could attach a pendulum to this, and this pendulum could swing, right? It could swing round in a circle. And then there's going to be reaction forces at that pin joint. Those reaction forces are going to have a component in the x and y direction. And then your normal force has to cancel those reaction forces as well. So this is not always true, okay? I know that you want to get into a habit of making these things really easy. N is equal to gravity. Not true. This is a dynamic problem. So don't think that this is always true. In this problem, without these changes, right? Without these changes, that would be true. What we want to do today in this video is we want to sort out the details on what the Coulomb friction force is. So let's clean this up and we'll get started. We want to come up with some claim about what the Coulomb friction force is equal to, right? We want to write out what this equals. Before we do that, let's just talk a little bit about the nature of friction. So here's an object. I've got my dry erase board eraser here on this surface, and if I push it, right, then this thing is going to accelerate and move. It's on the surface, which means we know that there's a little bit of Coulomb friction. And I'm going to reach down and I'm just going to barely poke it with my finger, right? I'm just going to barely touch it, the smallest little touch. And I'm going to apply very small forces to this. And if I do apply very small forces to it, it doesn't actually move, right? It didn't go anywhere. Why did it not accelerate? Newton's second law tells us that sum of forces equals ddt of k, which means if there are forces acting on it, then there has to be a change in the momentum. So why didn't the momentum change? We have an intuition about this. We know that things, they tend to stick to surfaces, right? And you push on it until you overcome that friction, and then it begins to move. That means that the friction acting on this eraser, and really everything, the Coulomb friction acting on it is in fact discontinuous. So there is a point where the object doesn't move, and then there's a point where the object moves. So let's define this Coulomb friction in a discontinuous manner. We said the friction is discontinuous. Let's write that down. Here's our block. We can do the free body diagram for it. We're looking for this FC Coulomb force. And let's say that what if the velocity is equal to 0 and the acceleration is equal to 0. So if the velocity is equal to 0, that means at this moment in time, the block is not moving, right? We can do the example of my eraser, and there's the eraser. It has no velocity. We're also saying that the acceleration is equal to 0. So that means whatever is happening with the block, right? I could be pushing on it, I could be giving little forces to it. The block is not in motion, nor is the block accelerating. This is called sticking. This condition, this is sticking. In this condition, then our Coulomb friction force, remember the force is actually a vector, so I'm going to put the bars on it. And by putting the bars on it, what I really mean, I'm talking about the magnitude now. The magnitude of the Coulomb force. So the magnitude of the Coulomb force is going to be less than or equal to mu sub s times n. Now you've probably seen this before, and I'm gonna put the norm of n here, or absolute value. So we're just concerned about the magnitude of the normal force as well. You've probably seen this before, where you take the normal force and you multiply by coefficient of friction. This would be coefficient of static friction, because again, the block is not moving. Notice that it's an inequality, right? Right now, it's less than or equal to this magnitude. Why is it an inequality? You might have seen it in the past where you just write equals to, right? And this is just equals to this. Well, here's the block, and the block is resting on a surface, which means it has a normal force. And then the coefficient of friction is, it's kind of it's a constant associated with the relationship between the object and the surface. It has a lot to do with the material properties, surface conditions, temperature, wetness, humidity, etc. All kinds of things can factor in. But this is a number. It's positive, right? So it's a positive number multiplied by n, which means this is a number. Well, if the Coulomb force, if the friction is equal to mu times n, then I ask you, why isn't my block moving? Right now, why isn't my block moving? It has n and it has mu, and if you multiply them together, you get non-zero. So if the sum of forces is equal to mass times acceleration, why isn't it accelerating? And it's not, simply because there is actually no friction acting on that eraser right now. If I reach down and I apply a little force to it, right, then this force, this Coulomb force, it actually will equal my input force. It will cancel the force that I apply to the object, and it will do that up to a maximum of mu s times n. So this is our sticking phase. What happens when I apply enough forces, when my applied forces equal mu s times n? What happens when the friction hits its maximum value? When it does, the velocity is still 0, but at this moment, at this instant, when the friction force hits its limit, hits its threshold, the body is going to start accelerating. So the acceleration now is non-zero. At this instant, we haven't accelerated yet, right? We haven't had a change in velocity yet, but we're breaking friction. So this first one was sticking. This is called stick-slip. This is the stick-slip transition. At this moment, at this one moment in time, then the magnitude of your friction force is exactly equal to mu s times n. Okay, next. So this exists only for an instant, right? Because if v dot is non-zero, then the smallest moment of time forward, it's going to make v be non-zero. So here now is v when v is not 0, which means the block is moving. At this point, you have Coulomb friction, you have Fc, and it's equal to, I'm going to write it this way. I'm not going to use the double bars, which means I'm not talking about magnitude. This is going to be the actual answer, the actual vector of Coulomb friction, and it's equal to this. So it's negative mu d multiplied by the absolute value of the normal force, and then it's V divided by magnitude of V. Now I could put some notations on this. Again, we know that this is body A. So I'm down here, I'm talking about the velocity of A, Coulomb friction on A, normal on A. Here is velocity of A, velocity of A. All right, let's talk about this claim right here. What exactly does this mean? So I'm not using the bars on the left. I'm saying we want the vector of friction. Mu d is just another coefficient of friction. You might see it mu sub k. This would be a dynamic coefficient. Mu sub k would be kinetic coefficient. It's just a different number than static, and it's less. The static coefficient is usually a significantly higher number. So this is just a number, again, positive. This is going to have a range of somewhere just over 0 to usually 1 or 2, something like that, depending on the materials. Look up wet glass on glass, for example, and these coefficients can actually get very large. So this is just a number. You're multiplying by, again, just a number. This is the absolute value of the normal force. This carries no direction. This is just a magnitude. So number times a number. V, the current velocity of A. So here's block A, and let's say that VA is to the right. Your block is sliding to the right. So VA has both the magnitude of the velocity and the direction. And then we divide that by the magnitude. This step right here, what we're doing right here, is we're normalizing the velocity vector, and out of this one part, you get a unit vector that points in the direction of the current velocity. By dividing by the magnitude, you lose the magnitude. This is normalized, and all it is, it's a direction. So if the block is moving to the right, and you did this calculation, if you did VA divided by magnitude VA, you would get x hat n for this drawing. If we say x hat n is to the right, here is xn and yn. If you were to perform this calculation, you would get x hat n. Okay, give it a shot, try it. So we have this last term carrying only the direction of the velocity, and then we're multiplying it by some scalar, and then we're taking a negative of it. Consider what the negative does. The negative reverses the direction of the motion. So if the body is moving to the right, if VA is in the x hat n direction, that means the Coulomb force is acting in the negative of that. It's acting in the negative x hat n. So what you will see when I do my free body diagrams is I tend to put friction terms positive. On the drawings, I will just put them as positives. I will put them as positives in my sum of forces equation, and then I will come back and I will take a description like this. If we assume, for example, that the system is in motion, that means I don't have to worry about this discontinuous part. I don't deal with these two. I just take this description and I put it in my sum of forces equation. This negative will automatically take care of the direction for me. So if I started here and I said, the name for this one. This was sticking. This was stick slip. So this one's just slip or slipping. Consider, I'm gonna erase some of this. Make sure you have it in your notes. If I wanted the sum of forces on body A, I would have said, from the diagram, I would have said FC in the x hat n, right? I would have assumed FC to be positive, and I'd have just written my sum of forces equation like this. I would then take this description and I would bring it here. I would say this is now equal to minus mu d, absolute value of n, VA divided by magnitude of VA, and this is in the x hat n direction. This is a perfectly valid way to write the friction term. Notice that it's in terms of known quantities. For example, mu d is known, VA, a magnitude of VA. These would just end up being the kinematics, which we know how to do. In this problem, that would be what? It'd be like Q dot, right? So this is Q dot x hat n divided by magnitude of it, which would just be Q dot. The N, the normal force, we could replace with something else. We said a minute ago in this problem, in this simple problem, that it was equal to this. We said, so I'm going to bring down the mu d. We said the normal force was going to be equal to the magnitude of, we said the normal force was equal in this problem to MAG. So MAG comes here, and then here is VA divided by magnitude VA in the x hat n direction. This is now the actual final answer for sum of forces. We got rid of this kind of unknown Coulomb force, right? It's perfectly fine to write it down for free body diagrams and put it in sum of moments, sum of forces, and then you have to replace it with what it actually is, which is this. And then we had the normal force. Well, this is an unknown reaction force, so we had to put that in terms of something that we know what it is. Mu d is now a constant, mass, gravity, these are all known. Velocities come from kinematics. That makes this expression fully known. There are no unknowns in this function, or in this expression. There are no unknown terms, which is where you want to arrive. Start with real simple declarations, put in definitions of it, and if you need to do in additional substitutions, you do those, and then now we're done. Okay, this is how I want you to handle Coulomb friction for this class. I'm going to make another video dealing with viscous friction, and of course, as we move forward with worked examples, we're going to start including this in that write-up as well. Okay, as always, stay safe, wash your hands. I hope you're doing well. I will see you next time.